Sorting. In this presentation, I'll go over why we need sorting algorithms, simple sorting algorithms, more complicated sorting algorithms, and distribution sorts. So the first is, why do we need sorting algorithms? Sorting can help avoid repeating data. Any repeating data will be placed together within a sorted array and can thus be easily removed if needed. Searching through the data is also made much faster, as instead of searching through every element in an array, you can do faster searches, such as binary searching, which doesn't have to look at every element and is thus much faster. Sets of data can also easily be compared when both sets are ordered. It's easy to see where sets have the same and different values. For example, in the first set here, it's hard to tell exactly what the difference is, and if you were coding a solution to tell the difference between these two arrays, you would have to iterate through every single element in O(n) squared time, which is very inefficient. In the sorted array, however, you can easily see that the difference is at the start, namely a 3 and a 2, and you could easily code a program to tell that this is the difference while everything else is the same. So simple sorting algorithms. The first is a selection sort. Selection sort works by finding the smallest value in an array and then placing that value at the start of the array. This is repeated until you have a sorted array. It's easy to code, however, due to its O(n) squared time complexity, it should not be used to sort large arrays, nor should it be used when the speed of the algorithm is important. Here is the pseudocode for a selection sort. As you can see, there are two for loops making the O(n) squared time complexity. We take the smallest element and we move it to the front, get the next smallest element, move it second to the front until we have a sorted array. Here is an animation explaining how it works. We search through it to find the smallest element. At the first iteration will be a 2, then a 3, and so on. And we keep repeating until we've sorted the entire array. The 5 was the smallest element, so even though it was in its correct position, we don't move it. And then we continue until it's sorted through the entire array, and at the end we'll have a fully sorted array. Like that. The next simple sort is a bubble sort. Bubble sort works by comparing every adjacent pair of numbers and swapping them if the larger number is positioned first. This is repeated n times, where n is the number of elements in the array. Once again, the sort's easy to code and has a time complexity of O(n) squared. Because more swaps take place in the selection sort, it's often less efficient and should not be used to sort large arrays. However, the sort can be fast when used on a nearly sorted array, assuming it's been coded to have a flag, which means that the sort stops once it knows that everything's sorted. Here's the pseudocode, and the difference between this and the previous one is that over here we keep finding the greatest element and moving it to the end, whereas in the previous we found the smallest element and moved it to the front. So in the animation, we'll keep comparing every adjacent value until we get the greatest one at the end. We then repeat continuously until we have a sorted array. And in the end, the array gets sorted. Then, more complicated sorting algorithms. The first is a merge sort. Merge sort works by breaking an array into subarrays, each containing an individual element. Every 2 subarrays are merged to make a larger, ordered subarray. Those subarrays are once again merged, and this continues until there is only one array, the final sorted array. The sort is much more complicated to code and has a time complexity of n log n, making it much better to use for large amounts of data. Here's a visualization. We split it up into 2 subarrays, and each of those are split into 2 subarrays once again. Over here, the 2 subarrays are compared. As 23 is smaller, it's placed first, and then 91. Over here, 8 is smaller, so it's placed first, and then 47. We then combine these with 8 being the smallest, then 23, then 47, and then 91. In the animation, you can see that every group is broken down into 2, and it's split back up. We keep making more subarrays and then merging them until we have larger subarrays, and in the end we'll have one subarray that's completely sorted, the final array. Another complicated sorting algorithm is a quicksort. Quicksort works by choosing a pivot and then separating every value into greater than the pivot from every value smaller than the pivot, making two smaller subarrays. At this point, the pivot's in its final location, as every element smaller than it is to its left and every element greater is to its right. Quicksort is then recursively called on those subarrays until every element is in its correct order. Quicksort is often considered the most efficient sorting algorithm. It's part of the hybrid sort used in the C++ sort function, introsort, and is also used in the Java arrays.sort function. The time complexity is, on average, O(n) log n. However, the worst case is O(n) squared, although this case is unlikely when pivots are chosen at random. To get rid of some of the flaws of quicksort, introsort and other hybrid sorts are often used. Now, the visualization here, red numbers are in their final position and the numbers that are lower are the current pivots. Of this first array, we randomly choose a pivot, here 15. We split it into everything smaller than 12 and greater than 15, 45, 32, and 81. As the left subarray only has one element, 12, it has to be sorted. We then look at the right subarray. A pivot is randomly chosen, here 81, and it's moved to its correct position. 45 and 32 are both smaller than it, so they're put on the left. Once again, we randomly choose a pivot, here 32, because the right subarray, which is only 45, has one element that's sorted, and this is the pivot, so it's sorted. And in the end, you have a sorted array. Here's an animation where the bright yellow element is the pivot. So we take 38, we split everything into greater and smaller than 38, and put 38 back where it's supposed to be. We then look at the left subarray, which is smaller than 38, and so on. This is recursively called until you have a completely sorted array. As can be seen, this is a very fast array, very fast sort, and works very well. Now, distribution sorts. Distribution sorts work by moving data from the input into multiple structures and then collecting them at the output, instead of comparing the values themselves. The first type is a counting sort. Counting sort works by counting the number of times every number is found inside an array and then displaying each number based on the number of times it was counted. The sort can be extremely efficient, but becomes less efficient the greater the size of the set of possible numbers is. For example, if you have 4 numbers that range from 0 to 1,000,000, the sort would not be efficient to use. However, if you had 1,000 numbers that range from 0 to 10, this would be extremely efficient. The sort also only works when every number falls within a particular set of possibilities. The time complexity is O(n plus k), where n is the amount of elements and k is the range of the possible values. Here's a visualization. We have an unsorted array and we know that every element will be between 0 and 9 inclusive. We make an array of possibilities of every number it could be, and we count each time everyone shows up. First we would get a 7, so we increase this by 1. Then 6, increase this by 1. And carry on until we have a counter. Once we have a counter, we add 1, 0 to the sorted array, 1, 1 to the sorted array, 1, 2 to the sorted array, 0, 3s, 1, 4, and so on until you have a sorted array. As you can see here, you count how many times each element shows up in the unsorted array and then put that back out in its correct order. And in the end, you have a sorted array. The second type of distribution sort is a radix sort. Radix sort works by splitting the numbers into buckets based on an individual digit. For example, using a base 10 radix sort, there'll be 10 buckets for the digits 0 to 9. First, the numbers are grouped based on their least significant digit, so in the number 13, the least significant digit will be 3. They are then combined back into an array, one bucket at a time. They are then sorted by the second least significant digit, and so on until the most significant digit. The sort is again more complicated to code than the earlier mentioned simple algorithms, and is a time complexity of O(n) times k, where k is the number of digits in the largest number. Here's an example. We have 5 base 3 numbers, and we look at 2 as 0, 0, 2. So the last digit will be the least significant. So first we put all the zeros to 1, so 120 and 20. Then we do everything that ends with a 1, 201, and everything that ends with a 2, 112 and 2. We then put them in this order. So 120, 20, 201, 112, and 2. We then sort this based on the second least significant digit. So everything that is a 0 in the second digit. And again, we put this down here to get 201, 2, 112, 120, and 20. Lastly, we look at the first digit, or the hundreds, and in the end we'll have a sorted array. Here's an animation where you split everything up by its final digit, you then recombine it, split everything up by its second last digit, recombine it, and so on. And here we're going through the most significant digit, the thousands in this case, and after this iteration we'll have a sorted array, as we do here. So extra information, the C++ has a built-in sort method using intro sort. The way you use it is as above. The two parameters here, where I have array and array plus size, are the start and end points of the array that you want to be sorted. If you want to see the animations with any specific values or anything else, you can go to this website here.